Good afternoon, everybody. Good to see you all again. So today's lecture will be given by Harish from Synopsys, and I did some homework before the lecture. I was asked to prepare this one slide, and you probably have known from the pre-lecture assignment and maybe from the previous reading that Synopsys is a big company in EDA, right, for designing circuit design and simulations. And this is a snapshot from a Synopsys website. They have many different services, different solutions to different industries. And of course, semiconductor companies, right? Whether it's a semiconductor foundry that makes chips, or you probably have learned from previous lectures, there are also fabless companies who design chips but do not fabricate chips. So Synopsys has been supporting those companies. And I didn't know until today that Synopsys has also been providing strong solutions to many other industries like automotive, aerospace, even financial services and medical services. So without further ado, it's my great pleasure to introduce Harish Balan from Synopsys to give us a wonderful talk on the things, exciting things going on at Synopsys. So welcome.
Thank you.
Thank you.
So the topic catchy enough for you? Billions of chips, trillions of dollars. Good afternoon, everybody. Pleasure to be back at Purdue. I was here the same class last year as well. And obviously, none of you have seen this movie before, so this movie has played before, exactly a year ago. And let me begin with the two most important words. Thank you. Thank you to my friend in the Office of Industry Partnerships, Matthew, for hosting me and Synopsys here today. We've had an incredibly great day. We always have great days when we show up here on campus. Thank you to all of you. You know, so many bright young minds here, and to be able to spend this time with you at this stage of your life and in your career, you know, it's very precious to me. It's something I respect a lot, that if I can get to influence one or two or maybe all of you for career pathways and academic pathways in semiconductors, then this whole trip would have been completely worthwhile. So thank you to you. And finally, thank you to the Purdue College of Engineering for doing an incredibly great job in semiconductor education in the United States. It's the leading program in the United States by a distance. And I really put this slide up here to give you a sense of how interconnected and how interdependent our industry is. No one person can fab a chip alone, and no one university can educate an engineer alone. It requires enormous amounts of collaboration with all the different players. And there are a lot of players, but it's I would call it, for lack of a better word, a very incestuous industry. Right? All of us have to work with each other to be able to get a chip out. So there's probably, I would say, in the whole world, there are about maybe 250,000 semiconductor professionals, right? In a population of about 6 billion people. So that's a pretty good responsibility to hold, and something we should be proud of. So congratulations to the College of Engineering at Purdue University. We have been partnerships. We've been partners with Purdue for many, many, many years. And it's only growing in leaps and bounds. And I can see that, you know, this class was a lot less full last year, and there's a lot more people now, so I'm very encouraged by that. So thank you again. All right, so this is me. I thought I'll give you a sense of who I am and my journey in this industry. And now, if you were an employer, or if you were, interviewing me for a job, then I would show all these things as a very nice, polished way of explaining what I've done with my life. But since you're a student, and I've been a student before, and I'm going to stop here and tell you something about me, the person behind that resume. A person who stood, who sort of sat in a room just like this 20-some years ago, and listening to corporate guys like me coming and talking about this and that. And I used to think to myself, what am I going to do with my life? Right? What is it that I'm going to do with all the stuff that I've studied. And I got to tell you, I wasn't a great student. I wasn't a bad student either, by the way, right? I was in the middle of the middle of the middle of the middle, if you can understand what I'm saying. And I'd taken a bunch of disconnected courses, just sort of, the ones that I felt would be the most important at that point in time. And maybe some of you have that motivation today. So I thought there's somebody like me sitting here today, and I thought I'd share that story with you. And I got a degree. I got my undergrad degree. I got my master's degree from University of Texas. And it came time to look for a job, right? So I would have taken any job. I had no money in my pocket. So I was basically, my only motivation was, how do I pay next month's rent? And the first job that came along was an application engineering position at a company called Compass Design Automation. And they said that we are in this electronic design automation space, and you've done a course in digital design. I said, yeah, sure, I've done that course. I don't remember anything, but I did do that course, right? And so I got the job, right? Because the field was pretty new. And they needed people with electronics degrees and things like that. So I got the job, and I started, my job was actually helping customers, with their problems. It was a tech support kind of role, going to different companies, trying to, solve problems that they had with our software. And in doing so, I was doing okay at it. I wasn't doing great, I have to tell you that, right? At least early on in my career, I wasn't doing very well. I wasn't doing badly either, right? But there was no purpose. I just didn't feel like a sense of, belonging or a sense of purpose. And then I visited this company called Medtronic. And I say this story a lot, even to many audiences that I speak to. Medtronic makes pacemakers and glucose monitoring equipment and medical electronics. And that was around the time my dad was diagnosed with diabetes. And when I saw this equipment, I said, wow, I'm actually working on something that has some greater application that could actually help my father. Right? And sure enough, at some point in his life, he got an implant which monitored his glucose on a regular basis, and it was built using EDA software. And that's when it was a great moment for me that actually I'm working. I have some purpose in my life. I have some purpose in my work. It counts for something. It makes the world a better place. It makes people's lives better. And that's really when I got fully involved in the industry, so it took me a long time. I was well into my 20s when I, felt a sense of purpose and a sense of belonging. So if I were to describe to you my life, at least my professional life, it was an accident. I just got into this role by accident, but I found my purpose later on. And I would like you to be a deliberate, find that purpose early in your life, right? And if that semiconductors work, great. If it's not, that's great too. But find it early on so that you don't kind of drift along for a while like what I did. But today I'm not drifting anymore. I am fully entrenched in what I do. And my background has primarily been in customer success. So that first job actually helped me. I started managing larger teams. I've lived all over the world. I've traveled to all over the place. And there's a great sense of purpose in what I do today, right? Working with students, working with universities, trying to deploy our software and build the next generation semiconductor workforce in the United States. So that's about me, right? A little bit about my company. Synopsys, the name stands for Synthesis Optimization. It's been around for 37 years. It was built on the premise that we can automate the design of integrated circuits, right? And we're still doing it. So it was run by the same guy that started the company until January of 2024. So he ran it for 37 years, which is kind of rare in Silicon Valley, if you ask me. Steve Jobs was probably the only parallel I could think of. And Art is the person who actually set up this partnership with Purdue back in the day, right? And so we're still doing it. We're still advancing the state of the art in terms of electronic design automation. And every single chip that is made uses Synopsys software. That's a great responsibility to have. It's a very humbling responsibility as well. Every single piece of electronics in your life has touched Synopsys technology in some way, shape, or form. Right? This is Art Tejius. He is our founder and was our CEO until the end of last year. And we set up this partnership with Purdue many years ago to build the next generation workforce, but also find opportunities for research, for education, and partner with professors and educators to advance the state of the art together, to bridge the gap between academia and industry. Right? This is what I do, by the way. I'm part of something called the SARA team, Synopsys Academic and Research Alliances, and we have 4 major programs. The first program is the University Software Program. We deploy our software in all the major universities in the United States. 200 plus universities in the US have our tools. And we look for educational partnerships. We sponsor, for example, the STARS program. You may have heard of that at Purdue. We sponsor 5 students there. That's one of our educational partnerships. We look for research partnerships. Purdue has the Center for Secure Microelectronics. We are research partners there. And the Academic Ambassador Program is keep looking for Purdue alumni within our company so that they can come into Purdue and retain those relationships that they've built while they were students out here. Right? So I'm an alumni of the University of Texas, and so I'd like to go back as an academic ambassador to UT and see what I can do for them, right, in some sort of win-win way. And with the passage of the CHIPS Act and so forth, right, there's a strong component of workforce development in my role today. Everything I do has got this lens of workforce around it. What is it that I'm doing that helps build the semiconductor workforce of tomorrow? So some stats for you. We're deployed in 230 universities, 46 out of the 50 states. So yeah, if you're from Mississippi, Hawaii, West Virginia, or I have to say Alaska, right? Then I probably want to talk to you about universities over there, right? For us, it's not a workforce development for us, by the way. Of course, we hire students, right? But not in the numbers that an Intel or a Texas Instruments or an NVIDIA or all these other companies that have come and spoken to you. We don't hire at that scale. But we have over 150,000 Synopsys users in the US. So anybody designing a chip, right? So that's the workforce that we enable. We have over 800,000, I think I had 700,000 technology users worldwide. Right? So that's what workforce means for us. Right? How is it that we can empower the next generation with our technology, state-of-the-art technology? Deirdre Hanford is currently deployed at the US Department of Commerce as the CEO of NatCast. It's an organization that's set up to disperse the $52 billion as part of the Chips for America Act. She was my boss at Synopsys for the longest time. She hired me 20-some years ago, and now she is with the US government. So we are very much invested in this CHIPS Act in the US. Right? We definitely want to reduce our reliance on foreign countries and bring back the manufacturing know-how that the US pretty much pioneered all those years ago. Right? And of course, Purdue I talked about. We have enormous partnerships here and very well embedded in the different programs. Right? Okay. Now, despite what you hear in the papers, right, of all the tech layoffs and things like that, we are living through an incredible time in the electronics industry. And I say that, with all humility, right? That the best time to be in electronics was 30 years ago. The next best time is today. Seriously, look at the electronic proliferation in your lives. Look at how many devices you're charging every day, right? And all of them require a chip. And with the advent of AI and smart everything, that's why my topic was billions of chips. There are going to be more chips than there are ants, right? You have to think about that, right? And at some point, we're just going to be limited by how much power we can consume on Earth. That's the number of electronics that we are talking, the amount of electronics we are talking about here. So we are tracking to a very high number. The semiconductor market is supposed to be, by the year 2030, will be $1 trillion. It's $650 billion today. So imagine, it's going to increase by almost 30% in just 5 years' time. So it's a great time to be. Yeah, I think you've done the right thing by showing up at this class, and I hope you continue your academic pathways in semiconductor technology, because it's a great time. You're going to find a great job, you're going to do well, you're going to build a pretty good career here. Right? All right, so where does Synopsys fit in? Like I said, this is a very interconnected, interdependent industry. Right? Synopsys fits in at the top left-hand corner here. Everything depends on everything else, by the way. Right? So the semiconductors, if it's a $650 billion industry, the semiconductor chips, the EDA and IP market is about $16.5 billion, and of which Synopsys is about $6 billion. We're the number one company in that space. Right? But without EDA, no chips could be built, obviously, and without chips, there's no EDA software. So we are all in a highly integrated supply chain here. Right? And that's the graph that actually shows you the kind of interconnections that we have. Every single chip, right, goes through all of these different stages in all of these parts of the world. So almost all roads lead to Taiwan. I think you know that already, right? But a lot of roads lead to Herzliya, Israel, Bangalore, India, Tel Aviv, to Munich, to Boston, to Austin, to Chandler, Arizona, Sunnyvale, California. And these are all these names that I mentioned is where all the chips get designed, manufactured, verified, packaged, and distributed. And I'm going to come back to this slide later on to show you what happens when this supply chain breaks down. Right. All right, so semiconductors, where are they? I think you know where they are. Well, they're everywhere, right? But let me show you exactly where. Right? Every one of you has one of these devices. At least most of you have an iPhone, right? So I'm going to tear it down for you. Right? And see, I don't think you've ever done that. Please don't try it at home. Right? It's not something Apple will void your warranty if you do that. But if you were to tear down the iPhone, what's the first thing you're going to see? The biggest thing you're going to see there is the battery. That occupies almost 30% of the real estate of your phone. That's true. But let's peel the onion a little bit more. Right? The next biggest thing is the A16 processor. That's the logic board. Right? And then you continue, and you're going to see these slides later on, so you may not be able to see all the fine print, but I highlighted a few things. So I'm going to show you the chip that actually counts your steps, or the chip that actually does the Bluetooth connections for you. This is a work of art, and you never get to see that. I know there was a time when I could open up a PC and flip out a graphics card, put a new one in there. Nobody does that anymore, right? But this is what electronics do. This is infrastructure, right? The innovation is not in all the apps and the touch screens that you press. The innovation is all in these chips here, right? And over 60 chips go into an iPhone, right? So I think I just took a guess on what some of these chips are, but one of them is a haptic engine driver on the top left-hand corner. That's the one that actually does the touch screen and gives you that feedback when you're playing Candy Crush and things like that. Right? There's an audio amp in there. Here's the chip that actually counts your steps. This comes from a company called Bosch. There's about 20 different suppliers that supply chips to the iPhone. It's not just Apple. I don't know how many of you have actually seen this teardown before, but you have? Okay, good. So this is an iPhone that's completely deconstructed. Right? Now, the reason I show you that and why mobile electronics are battery dominated, I think you understand this, right? You see your phone getting hot. The most important overarching challenge in electronic design today is power. How do you conserve power? And so I'm going to pose that question to you. If I were to come to you and say, hey, listen, your PG&E bill, well, PG&E is our California company, but your utility bill is just too high. I want to reduce it by 25%. What would you do? How would you go about that, solving that problem? You're going to start thinking about power in usage in every part of your life, from the time you get up till the time you go to the bathroom, till when you leave the house. You think about power all the time and try to see, okay, where can I conserve? The same thing happens in chip design as well. So from the time you architect a design till the time you specify, till the time you verify, till all the different operations that you do, you try to figure out where can I reduce power. And the more, chips are getting more and more complicated. They're using more power. Your apps are getting more, bloated. So power will always be a limiting factor, right? So, one of the techniques, right, is called clock gating. What is clock gating? It's nothing but, when you leave the room, you turn off the lights. It's the same thing. It's exactly the same. That's this is the way I remember technical concepts. So I'm trying to make it simpler for you to understand it. But there are many such power management techniques that you can model in software and actually reduce the power consumption of a design. So I'm going to show you one of them. Right? We have something called the low power flow, right, for system on a chip design. And it's all of these terms that you're seeing, architectural exploration. These are all the different steps that a design goes through. And in each of these steps, we try to optimize for power, right? Try to see what types of circuits will use the least amount of power. Let's try to do an always off technique so that we use power only when we need to and things of that nature, right? So when we apply such techniques, let me give you the impact of a technique like that, right? So here's an example for planet Earth. The global impact of energy consumption from mobile devices. So let's say there are 1.5 billion mobile phones on Earth, right? And each of them uses 6 watts of power. You're looking at 19,500 megawatt power plants. You need to power all this stuff. It doesn't come for free, right? So imagine trying to shave just like a 0.5%. Or 1% or 2% or 3% of that big number. What kind of difference would it make? Right? So here's an example. You apply our low power flow to the same iPhone design. We were able to get a reduction of about 4.5%. You know what that means at the grand scheme of things? It's 1 power plant less. This is the impact of what we do. We're able to model these effects in software so that you can, you have it's like a ripple, when you throw a pebble inside a pond, you see the ripple effects will last forever. This is exactly what we do with our low power flow. Right? All right, before I get to the next sort of technical challenge, I'm going to ask you a question, right? How many of you have used ChatGPT? Yeah, all of you, of course. You use it to do homework, right? I'm sure you do, right? Of course you do. Yeah, I've used it quite a bit too, right? And look, everybody's using it, right? Everybody's using it. Everybody's trying to figure out, what can we use AI for, right? Is it? Somebody told me AI stands for artificial inflation, right? Is it all hype? Is it all like a big scam? Actually, it's not, right? We're all trying to figure out. What is AI, first of all? It's basically an applied heuristic. Right? You're taking the knowledge of an expert and you're trying to give it to multiple machines. And you're able, so the better the machine is trained, the better your results are going to be. So a large amount of data, infinite number of machines, and that's AI, really. Right? So we are trying to figure out what AI is and what it means for chip design, and we are seeing orders of magnitude improvement. Right? So here's an example. We have a technology called DSO.ai. DSO stands for Design Space Optimization. Right? We are trying to figure out what are the 4 major vectors in chip design are power, performance, area, and cost. Right? Those are the 4 things. There's no other thing. Right? And if we are able to optimize these 4 parameters, you'll get the best design optimized for that condition. For example, if it's a mobile application, it has to be power and area. If it is in a data center application, it has to be performance, right? And so we can use these design space explorers, right? Apply AI techniques to them, and just traverse through multiple hundreds of designs to try to get the best result possible. And we are seeing very encouraging results here, right? So we are able to take the knowledge of an expert and literally democratize it across a large teams of people. So prior to this role, I used to be an application engineering manager where we used to work with companies like Qualcomm. Now I'll tell you what Qualcomm does. They used to have teams of people. They tried to apply recipes to try to get the best performance, power, and area, right? Now we can do the same thing with just one person. Right? Just because you have the techniques and you have infinite compute. So we are getting incredible results, and I actually have some of these results here to show you. So the problem statement here for this for our AI application is achieve the lowest power by maintaining total negative slack less than a certain number. And the application kind of thrashes around, right? The first few times it's not been trained. So it thrashes around trying to find the best number. But once it's been trained, right, it gets you a result that's 30% better than the best possible result that's been obtained by a human. That is the power of AI. So it's real. It's not artificial inflation. It is real. It's it's something that's here to stay. And as long as models are well trained, and the compute can support that, it will help you in all aspects of life, not just in chip design. So we are looking at AI not only for chip design, but how to write code, how to optimize our processes, how software engineering techniques, all of these different in our hiring processes, and in almost every aspect of our business. So it's real, it's here to stay, and it's something that's going to only increase in terms of usage over time. Right? All right, so we actually pioneered this. Our AI tool has been in existence for more than 5 years, before AI was a thing, right? And we've been obviously experimenting with it. We can do many different characteristics like best congestion, best timing, best area, et cetera, et cetera. And in every one of these areas, we are seeing dramatic improvements. Right? So then people ask the question, okay, what, AI can do all these things. What are humans going to be doing? Right? Am I going to get a job? Or look, let the machines do what the machines can do, right? I mean, let humans do what we are good at. We are good at taking disparate concepts and applying them to a completely different application. No machine can do that. Right? And we are curious by nature. We are inventive by nature. Right? We are able to adapt to different conditions very well. Again, no machine can do that. So no machine is taking over this. Right? You will always have co-pilots and assistants and AI type programs that assist you, but they're not going to take over the world. Not in my lifetime, not in your lifetime either. Right? All right. So, like I said, we are the first one to introduce AI in chip design, and we are going to continue to advance the state of the art as we go into the future. Right? All right. The next sort of technical challenge that I'll talk to you about is something called what we call silicon lifecycle management. Right? This is a new it's a new paradigm, really. Previously you bought some gadget, and it lasted for 2-3 years, and it was gone, right? And you replaced it with the next big thing. But today, if you install a pacemaker, you're not getting rid of it after 2 or 3 years, right? If you buy a Tesla, you're not getting rid of that after a few years. Sorry, let me go back, right? And so you need to be able to model effects of aging electronics. What happens in harsh environments? What happens to a pacemaker when you go 30,000 feet up in the air? Right? These are things that you can model in software. Right? And that is something what we call a silicon lifecycle management. We instrument designs with sensors in them. Right? And those sensors keep collecting data. right? For us to be able to, to analyze them in the field, in the factory. So that the next time the Tesla crashes, right? They have these black boxes. There's basically like a forensic analysis. Hey, what exactly happened, right? And when we get that kind of insight, you're able to get the next generation of chip to be better and to be able to handle those kinds of conditions. And that's exactly what silicon lifecycle management is. This is also an area that is brand new in the semiconductor industry. It's going to continue to stay because electronics are going to be more and more pervasive and more critical to your applications. This is not a phone that you get rid of every couple of years, right? This could be a life-changing device or life-transforming device like that glucose monitoring equipment that I talked about. Right? So this is another technology that we're working on. Again, you can model this only in software, and so that most of the problems can be found well before the chip is actually fabbed. Right? And by the way, it is extremely expensive to find and fix problems in the field. After the fact, fixing a problem is very, very, very expensive. Yeah, you hear of some of these, Toyota recalling all these cars. Just imagine how much money we're talking about here. And imagine if those problems were found in software during simulations or during verification. Right? So that's exactly what we do here. Right? We instrument the design with sensors, and we collect data while that device is operational, and so that we can take that data and use it to build a next generation device. So here's an example of the largest chip that's ever been built. Right? It's a company called Cerebras. It's an AI processor. It's not NVIDIA, by the way. It's I know we've heard a lot about NVIDIA lately, but this is the largest chip that's ever been built, and it was built using large part of it was built using Synopsys technology. And here the gentleman here gives us a commendation about the SLM or lifecycle management techniques that they use to be able to fab this chip. So this chip is in production today. Something about our products, I think you should just look it up or look through this presentation later on. But the Synopsys Digital Design Family has been around for a long time. This is pretty much a gold standard in the industry. Right? Almost all designs go through this particular flow. And many of these tools have been around for a long time, but we continue to obviously advance the state of the art. Right? And another area where you probably may not know what we do is on IP blocks. For example, the USB core, the PCI Express core, the HDMI on your laptop. These are all IP blocks that are provided by Synopsys. Right? You don't have to reinvent the wheel. What most companies do is they put all these IP blocks together, they stitch it together with their own creativity and with our EDA tools. And that's how a chip gets fabbed. So we are one of the largest providers of IP in the world. Right. All right, so I told you about myself, my company, some technical challenges. Let me also talk about the second part of my presentation, second part of my title, which says trillions of dollars. Right? So we talked about the billions of chips, but there are trillions of dollars at stake here. Right? And I showed you this graph before about how our supply chain is so deeply interconnected. What happens when it breaks down? When it breaks down, entire economies can grind to a halt. That's how critical electronics has become. It wasn't always this way. Right? So here's an example. That's actually a photo taken from outer space of a bunch, 100,000 Ford trucks waiting for chips to be delivered from Taiwan. Right? And I don't know if you remember, but about 3 or 4 years ago, you suddenly couldn't find any cars, you couldn't find dishwashers. Why? Because exactly why. Right? The supply chain got broken. And suddenly people realized that, wait a minute, right? All the stuff we depend on for our daily lives and living is we need to control that. We need to control, otherwise we're just going to be held hostage. Right? So that's exactly the reason behind the CHIPS and Science Act. President Biden, he mentioned that this is infrastructure. Infrastructure is not the bridges. I mean, of course, it's also the bridges and the highways and the roads and all that stuff. But this is as much infrastructure as anything else. If we don't control the supply chain, if we don't understand the supply chain and where things could go wrong, we are in for a world of hurt. Right? And we may lose our competitive edge as well. Right? So this is exactly $52 billion. This is the most any government has spent or apportioned in the history of the world for any one industry. So this gives you a sense of how important it is, right, for all of us, right, that we succeed here. Right? And so clearly it suddenly, from a relatively obscure industry, it suddenly became front and center in everybody's mind. Right? And suddenly we got, of course, Purdue has always had a fantastic program, but suddenly we got universities coming out of the woodwork and saying, we want to have a semiconductor program and this and that, right? But that's great. That's exactly what we want. And we're obviously very excited about, all this buzz that's taken place. It's like make semiconductors cool again, right? Is that a good thing to say here in Indiana? Right? No, I won't go there, right? But that's exactly, my point was this is infrastructure, right? $52 billion was allocated, and a bunch of that money is actually being spent right here in Indiana. Right? In terms of jobs, right? So most semiconductor jobs pay very well. Right? So for every one job, they're over, it accounts for about 1.6 million indirect jobs, and there's 277,000 semiconductor professionals in the US. And they, in turn, influence about 1.6 million, allied and related industries. So it's a pretty important, it has a large footprint in terms of employment in the United States. Right? And if you look at by state, almost 49 states in the US have some type of semiconductor industry in there. Right? I know Indiana is not up on this list, but it will be. Maybe next year when I'm here, I'm going to be putting it up on that list. But clearly, every state government sees the potential of this industry, right? In terms of job creation and in terms of value creation, right? And also, obviously, securing our supply chain. Right? I'm going to let you just read what I highlighted, not all the other text, but I know as a student I cared about this. I hope you care about it too, unless you are Elon Musk or something like that, right? But this is an important part of why we do what we do, right? So this is a good time to be in semiconductors today, right? And it's front and center on everybody's mind. You can get paid very well. I'm sure you're not going to have any problem finding a job. So I think that's something that I should leave with you. Right? All right. So Dr. Wu asked me to put together a list of jobs that we have at Synopsys and what is it that we look for. So here are a couple of jobs. The three positions that I sort of highlighted: a design engineer, a product engineer, and an application engineer. And depending on your personality, frankly, not your degree, but really about your personality, you would fit into one of these things. Now, I'm definitely not an R&D person. I'm a people person. I get a lot of energy from others. So I'm an application engineer by instinct, right? But if you are customer business focused, then you're kind of at the right-hand side of that spectrum. And if you are more product and technology focused, then you're on the left-hand side of that spectrum. So a design engineer is expected to work on products and technology and go deep. An application engineer is expected to go broad. Right? I should know how everything works with everything else, what goes into this, what goes out of that, whereas a design engineer looks at the vertical stack. Right? So it's basically deep versus broad. Right? And a day in the life of an application engineer. So this is my first job. This is what I did, right? Helping a customer, tape out an example, being a champion for that customer inside the company, right? Making sure that our tools are being used, deployed, right? It's not enough that Purdue has our software. That's not enough. I want people to be using it. I want people to give us feedback, improve the software, make it happen, build products with it, right? So this is what application engineers do. We train, we become the customer's champion inside and outside the company. And a design engineer looks typically, has a bachelor's or master's degree. They work on, deep technical areas. They build, features in the product. They make sure that it is robust, right, when it is used in the field. Debugging skills are very important, as a design engineer. Scripting skills, coding skills, problem-solving abilities. These are the skills that they look for, right? Basically converting ideas into products and features. So this is my last slide. Right? In summary, semiconductors are everywhere. Right? It's in your life. Right? And it's a complex, interconnected, but exciting industry. It's changing all the time. A year ago, ChatGPT had just come out. Today, we have literally thousands and thousands of applications. Next year when I'm here, add one more zero to that, right? So it is constantly evolving. It's a great place to be. You'll never get bored, right? 28 years later, I'm still around. I'm still learning new things. It's a great place. I mean, it's always refreshing itself. And then in terms of economics, it's front and center in everybody's mind. There are senators who have no idea what electronics is, but they now know how to spell semiconductors, right? So it is front and center in everybody's mind. And I don't think you'll have any problem finding a good job and building a very exciting career for yourself. So let me end again with the two most important words. Thank you all for your time here today, and it's been my pleasure to be back here at Purdue. So folks, I don't come empty-handed, right? So if you have a question, then I have some goodies for you, Synopsys branded goodies for you. It's a mobile phone holder and a pop socket. I know when I was 19 years old, I would have liked one of those. So if you have a question, please fire away, and I'd be happy to share some of this stuff with you. Right? Yes. Please state your name and your question.
So you brought up these new tools that Synopsys is being using AI to make the nitty-gritty of repetitive processes, the more specialized things occur more frequently. So my question is how does that impact the job market for chip designers? Does that make the job of a chip designer more higher end, being more problem solving?
Yes.
Or is it more about
no. So we see, look, back to that. I think. Look, just for the benefit of the folks, the question is, if AI can do all this stuff, what will the job market? How will it affect the job market? And what skills? Look, creativity is a human condition. Right? It's not a machine condition, right? No AI creates. I mean, as creativity comes up with new ideas. So the skills that we would require pretty much the same, the problem-solving abilities. But things like, I can tell you things like coding, for example, that will evolve. Yeah, there was a time when during my dad's time, they added numbers using logarithmic tables. Now, who uses that, right? Nobody uses that. Right? You use your phone to do that, right? So you worry about bigger things. So same way, a lot of the grunt work will get taken out. You wouldn't have to write Verilog for a 2-bit adder or a multiplexer or whatever. All these, the machine will be able to do that. Similarly, the example I showed you about recipes, right? Trying to find the best performance. That's brute force. You just keep trying different parameters to see, and then write it up in an Excel spreadsheet. You wouldn't have to do that, right? Because the machines can do that. But now you'll be able to, think beyond that, right? So the idea is, as humans, we continue to evolve. And we are, and I think that our creativity, our problem-solving ability, our capacity to adapt and innovate, that will never go away, right? It will never go away. No machine can take over that, right? So I remember when I started out, people used to say, oh, you know what, robots are going to change the world. Well, we see robots running around at Purdue. It's not taking anybody else's job, right? So yeah, thank you for your question. And here's something for you, right? Let's give him a couple of these things, right? I want to finish up all this stuff. Let's give him the pop socket and the mobile phone holder. Thank you for your question. Yes, sir. Yeah.
So we are all quite early in our careers.
Yes, indeed.
Do you have any advice to help us succeed either in Synopsys specifically or in the semiconductor industry more generally?
Okay. Well, that's a great question. The question is, do you have any advice for us to succeed in the semiconductor industry specifically? Identify which areas. Even though it's a fairly small space, there are many moving parts here. There's design specification. You could be a design engineer. You could be a manufacturing engineer. I know the STARS program here at Purdue has 3 different tracks. There's a design track, there's a manufacturing track, there's a packaging track. All 3 are technical jobs, right? And there's no one. Let me tell you, there's no bad job, right? It's not like one job is better than the other job, right? It's the job that fits you. You want to find something that works for you in terms of your personality and your IQ and your EQ. Find that job. Don't follow your wallet, right? That's one piece of advice, right? And follow your personality and your passion. I think that not just your degree. You'll probably find a job somewhere, but look at what you're going to be doing, And I think the first couple of years, maybe first 2 or 3 years, there's no bad job. If somebody asks you to sweep the floor, you sweep the floor, right? Be the best floor sweeper you could be. Right, and that's how you build something, right? You don't, and that's how new opportunities open up, right? I've seen many folks, especially early in their career, kind of, flitting around, right? Oh, this didn't work for me. Let me try something else. Don't do that. Try to stick it out. Stick it out to at least get promoted once, and then leave. Then do something else, right? Excel in something, and then that would be my advice. Yeah. Well, easy to give advice, right? It's hard to follow it. Yeah. Thank you for your question. Yeah. Here's something for you, right? Yeah. Oh, you got it already. Okay, come on. All right. Yes, please. Yeah.
To add on to that question, what soft skills do you think are important, especially for
good communication skills? Yeah. So this is, we are in a global workforce, right? Your competition is not the person sitting next to you here. Your competition is a person who's sitting in Herzliya, Israel right now, or in Seoul, Korea, or in Singapore. Communication skills and cultural, how would you say, right? Understanding of world cultures. I think that's a very important skill to have. Right? If you know another language, or if you're able to connect with people easily, I think that's an important skill. Teamwork. Most projects, nobody does anything alone, right? Nobody. I'm glad to see actually at Purdue we have so much collaborative types of projects here. Please, hone your collaboration skills, because you'll have to work in teams. You'll have to be able to communicate your ideas, and sometimes speak up about a minority position. Many times early in your career, you kind of feel you want to say something and you don't. You feel like intimidated by the environment. I think you should speak up, and I think people appreciate that. Right? So so in terms of soft skills, the ability to present, the ability to be culturally sensitive, and work in teams, I would say those are very strong indicators of success. Yeah. Appreciate your time. Thanks a lot. My best part of my day. Thank you very much.